Hey everyone, welcome back to another explainer. So if you've ever stood there just completely in awe of a massive excavator lifting, I don't know, tons of earth without breaking a sweat, or watched an automated factory line move with that relentless pinpoint precision, and you found yourself wondering, what exactly gives these machines their immense power? Well, you're looking at the absolute magic of hydraulics. Today, we're going deep. We're exploring the literal cardiovascular system of heavy machinery, the hydraulic pump.
All right, here's our roadmap for today. We'll start with pumping theory, move into pump classification, and explore gear and low pumps. Then we'll examine the axial piston pump, look at variable flow control, and finally wrap the whole thing up with some troubleshooting.
Okay, let's kick things off with Section 1, Pumping Theory.
Now, before we even think about moving metal parts, we really have to understand the fundamental physical challenge of moving liquid under extreme pressure and exactly how our machines actually overcome it. So, to ground ourselves, let's define what we're actually talking about here. A hydraulic pump is essentially a combined pumping and driving motor unit. Its entire reason for existing is to take hydraulic fluid, which is mostly just specialized oil, from a storage tank and forcefully deliver it to the rest of the hydraulic circuit. It acts as the primary driver. It's the thing that establishes the flow and literally wakes the entire system up.
And before we dive into the internal mechanics, I really want you to appreciate the sheer optimization of these things. When we talk about power efficiency, the ratio of output hydraulic power to the input mechanical or electrical power, these pumps aren't just good, they are extraordinary. We're talking about frequently hitting a staggering 90 to 98% efficiency. Almost zero energy is wasted.
But despite all that incredible efficiency, they do actually have a mortal enemy. It's called cavitation. Cavitation is the highly dangerous formation of tiny vapor cavities, basically little voids, in a liquid. And this happens when the fluid is subjected to a super rapid drop in pressure. Now, the real danger isn't the bubbles themselves, it's what happens next. When these voids travel into a higher pressure zone within the pump, they implode. This implosion generates these intense, microscopic shock waves that can literally pit and tear the solid metal of the pump apart over time. It's brutal.
So, to prevent that destructive cavitation, engineers have to be smart about system design. Think about a setup where the pump is placed above the fluid storage tank. The pump creates a negative pressure at the inlet, sure, but it's actually the atmospheric pressure pushing down on the fluid in the tank that forces the liquid up that inlet pipe. It's brilliant. To prevent those rapid pressure drops that cause cavitation, this pump lift distance must be kept as small as practically possible.
Moving right along to Section 2, Pump Classification.
We really need to draw a hard line here because there are two entirely different families of pumps. On one side, we have non-positive displacement pumps. Now, these are fantastic for high-volume applications, but they operate at a low pressure and their delivery varies wildly depending on the pressure at the outlet. On the other side, though, we have positive displacement pumps. These are the absolute heavy lifters of the hydraulic world. They use super tight internal seals to trap and deliver exact, constant volumes of fluid at incredibly high pressures, completely independent of whatever pressure is fighting back at the output port.
Let's consider a classic non-positive displacement model, the centrifugal pump impeller. It uses rotational kinetic energy from an engine to just fling fluid outward to the periphery. Because it relies on centrifugal force instead of tight mechanical seals, it is perfect for moving massive volumes of liquid rapidly. But it's fundamentally limited to low-pressure applications, usually maxing out around 20 to 30 bars.
Contrast that entirely with a positive displacement or reciprocating pump. This acts remarkably like a four-stroke engine in your car. A piston moves down, opening an inlet valve to draw in a very specific volume of fluid. Then it moves up, the inlet closes, the outlet opens, and that exact volume is pushed out. Because of this sealed, rigid mechanical action, it delivers a constant volume with every single cycle. It doesn't care how much resistance or pressure is waiting at the output port, it just pushes it through.
All right, Section 3, Gear and Lobe Pumps.
The external gear pump is an absolute workhorse in the industry. It features two meshing gears inside a housing. As the gears rotate out of mesh, they create a vacuum that draws fluid in. That fluid is then trapped between the gear teeth and the outer casing, carried all the way around the outside, and forced out the high-pressure discharge port as the teeth violently mesh back together. It's incredibly effective, though I should mention it does have one notable drawback. The high pressure at the outlet and low pressure at the inlet creates an unbalanced side load on the gear bearings, which kind of causes wear and tear over time.
Now, what's really fascinating is how the lobe pump takes that exact gear concept and adapts it for a totally different industry. The lobes rotating inside the housing do not actually make contact with each other. Instead, their rotation is perfectly synchronized by external timing gears. This gentle, non-contacting pumping action makes it a total superstar in the food, beverage, and pharmaceutical industries. You can literally pump delicate solids, I'm talking whole cherries or olives, right through this machinery without crushing or degrading the product at all.
We'll wrap up our gear tour by highlighting the internal gear pump. The absolute star of this design is the distinct crescent-shaped seal located right in the middle. Fluid enters and travels between the teeth of a large outer rotor and a smaller inner idler gear. That crescent perfectly and efficiently divides the liquid, acting as a dynamic seal between the suction and discharge ports right before the teeth mesh again to force the fluid out. It's just a brilliantly compact and versatile piece of engineering.
Moving into Section 4, the axial piston pump.
So if gear pumps are the reliable draft horses, the axial piston pump is the high-tech sports car. It represents the ultimate solution for precise, dynamic, and extremely high-pressure fluid volume control. Let's break down its continuous operational cycle into 4 steps. First, rotation. The drive shaft spins, causing the entire cylinder block and its internal pistons to spin right along with it. Second is the intake stroke. As they rotate, the pistons are mechanically pulled outwards, creating a low-pressure vacuum that sucks hydraulic fluid into the cylinder. Third is sealing. A distribution plate isolates the inlet, securely trapping that ingested fluid. And finally, the discharge stroke. The pistons are forced violently back into the cylinder, decreasing the volume and blasting the trapped fluid out into the hydraulic system.
Which perfectly sets up Section 5, variable flow control.
You might be wondering, how exactly are those pistons forced in and out as they spin? Well, the secret sauce lies in something called swash plate mechanics. This is the brilliant mechanism that allows this pump to actually vary its fluid displacement on the fly. The swash plate is essentially a flat disc that the ends of the pistons glide against. And the sequential logic here is just stunning. If that swash plate is at a 0 angle, meaning it's perfectly perpendicular to the pistons, the spinning pistons don't move in and out at all, resulting in minimum stroke in 0 flow. But if a control mechanism tilts that swash plate to an increased angle, the pistons are literally forced to ride up and down that slope as they spin. Therefore, a greater tilt directly equals a larger piston stroke, which results in a much higher volume of fluid expelled into the machine.
And finally, Section 6, troubleshooting.
Let's pivot away from pristine mechanical theory for a second and step into some gritty, practical reality. Imagine you're an industrial mechanic, and you've just been called in to diagnose a sluggish, struggling machine. Assuming the filters are clean and there's no visible damage on the outside, we have to look inside. The crucial point here is identifying 4 hidden culprits. Number 1, internal leakage. This is often caused by worn piston rings allowing high-pressure fluid to just slip backward. Number 2, internal friction. This happens when sticky, varnished components sap the pump's mechanical efficiency. Number 3, control issues, like a faulty valve failing to properly adjust that swash plate angle we just talked about. And finally, number 4, air entrapment. This happens if air gets sucked into the suction line and it results in a terrible, spongy, and totally erratic response from the controls because those air pockets are actually compressing inside the pump.
Honestly, understanding these mechanical hearts gives us such a profound appreciation for the massive, complex world built around us, which leaves us with a pretty fascinating thought to ponder. As external electronic controls, load-sensing algorithms, and digital joysticks become infinitely more advanced, how will the dynamic, split-second precision of the swash plate continue to shape the highly automated, energy-saving heavy machinery of tomorrow? Because one thing is for sure, the mechanical heart is only getting smarter. Thank you so much for joining me on this explainer, Focus Learners, and I will see you in the next one.